Happy New Year and welcome to Chapter 10, where we talk about things that go boom, specifically nuclear energy and radioactivity. So we're going to start by talking about what radioactivity is. Radioactivity is the process in which an unstable atomic nucleus emits charged particles and energy. So remember, a nucleus is the positively charged center of an atom that has protons in it and it has neutrons. And the electrons are located outside of the nucleus. Just a little recap. Now, an atom containing an unstable nucleus is called a radioactive isotope, or radioisotope for short. So remember, an isotope is an atom of the same element that has the same number of protons, but a different number of neutrons. And it turns out the bigger the element, the more likely an isotope is going to be unstable, or a radioisotope, and break down fairly quickly and release radioactive decay. So these radioactive isotopes decay or fall apart. And when I say fall apart, I actually mean that the nucleus of these atoms fall apart. And when this happens, atoms of one element can completely change into atoms of a different element. And as you remember, what defines what an element is the number of protons. So during radioactive decay, the amount of protons inside that nucleus actually changes. So you can see here we have one isotope. This nucleus has protons and neutrons in it, and it can fall apart into a much smaller one while emitting particles and energy. And that's exactly what happens. So nuclear radiation is what's released from these nuclei when they decay. It takes the form of charged particles and energy, and it's usually one of three common types. There are alpha particles, beta particles, and gamma rays. Alpha particles are the least powerful of the three, and they're very common. So an alpha particle is a positively charged particle made of 2 protons and 2 neutrons. So if we draw that, we've got 2 protons and 2 neutrons. And if you think about it, okay, what element has 2 protons? Helium. So basically, an alpha particle is a helium nucleus. When a large nucleus that is unstable decays and emits alpha particles, it's basically getting rid of a helium nucleus, and then its own nucleus will become that much smaller. Now we can write a shorthand symbol for an alpha particle. Sometimes we write it this little squiggly fish looking kind of thing. This is the Greek letter alpha. Or if we want to be more specific, we can write this symbol. Now this is a special way to write information about elements. He is the symbol for helium, and then the 2 and the 4 represent the atomic number and the mass number. Remember, the atomic number is the number of protons, and the mass number is the number of protons and neutrons together. And we can write this kind of symbol for any element, any isotope that's out there. We write it like this for an alpha particle because we said that an alpha particle is basically just a helium nucleus. So that's how we represent it. Now, an alpha particle has a pretty high mass. It's got 4 significant subatomic particles in it, so it's pretty big, which means it's not going to move very fast, and it has pretty low energy and low penetrating power. That means alpha particles, alpha radiation, can be stopped by something as thin as a piece of paper. It's not going to penetrate that piece of paper, and so alpha particles really don't affect human beings all that much because they really can't penetrate into our skin or our cells far enough to do a whole lot. The next step up is beta particles, and beta particles are basically just a negatively charged electron. Now it's weird to think about a nucleus made of positive protons and neutral neutrons breaking down into an electron, because the electrons are found outside of the nucleus. But what happens with beta decay is that a neutron actually breaks down into a proton and an electron, and that electron is then emitted. So the symbols we can use for beta particles are this little bee with a tail. This is the Greek symbol beta. Or we can use the same kind of symbol we did last time. This time we're going to use that symbol for an electron. So basically this symbol means E for electron, the charge is down here, -1, and the mass is up here. Remember, we said an electron is so small compared to a proton and neutron, it basically has no mass, which is why there's a 0 there. Now, because beta decay has such low mass, it can move pretty quickly, and it has medium energy and medium penetration power. Beta particles can go right through a sheet of paper where alpha particles can't, but they do get stopped by thin pieces of metal. So these beta particles can interfere with us as human beings because they can penetrate deeper than alpha particles. The third kind of radiation that we're going to learn about is called gamma rays. And gamma rays are neutral, they don't have a charge, and they are rays of pure energy. They don't have any mass or matter associated with them. These are usually found alongside either alpha or beta particles, because if a nucleus is breaking down, there is going to be some exchange of mass, some exchange of matter. So when a neutron breaks down or a nucleus breaks down, alpha and beta particles are emitted, and if that's a really violent decay, gamma rays will also be emitted. And gamma rays have very, very high energy and penetrating power. Gamma rays can go right through that piece of paper and that thin sheet of metal that stopped the alpha and beta decay, but it can be stopped by a really thick lead wall. Now, that is usually what we think about when we think about radiation, and containing radiation is having these really super thick lead-lined walls, and that's because of gamma rays. Gamma rays can penetrate enough and have enough high energy that they can significantly impact the DNA inside the cell of a human being or plant or animal, which is what makes them so dangerous. Now, we can write these decays as nuclear reaction equations. And just like in math, we can set up an equation using the symbols to represent what the radioisotope breaks down into. For example, a really common radioisotope is uranium-234. Remember, the symbol here represents the element name. This number, the bottom number, is the atomic number. And then the top number is the mass number, and this tells us what isotope it is or how many neutrons it has. So it turns out that when uranium-234 breaks down, it loses an alpha particle. Remember, we represented the alpha particle as this, and we end up with thorium-230. And that makes sense because we lost 2 protons, so 92 minus 2 is 90. And we also lost 2 neutrons, so we lost 4 particles altogether. So 234 minus 4 is 230. So this side of the arrow, this side of the equation, tells us what our radioisotope is, and this side of the equation tells us what we get. So uranium-234 decays into thorium-230 and alpha particles. Now, how does radiation affect us? Well, we actually interact with nuclear radiation every day in the form of background radiation. Background radiation comes from everything. It comes from rocks in the soil, air, water, plants, and animals, but these levels are usually really low. For example, radon is produced in the ground inside certain kinds of rocks. And that radon, those radioisotopes of radon, can seep upward through the ground and into certain homes. Now, usually those levels are really low, and it doesn't affect us at all. However, if a lot of radon is being produced in the ground, that can increase the levels of radiation, and it can damage the cells and tissue, and as I said, sometimes the DNA in our body. That's why we have radon detectors in certain buildings, like schools. We need to know what the radiation levels are to make sure that everyone is safe. We can also detect these radiation levels with things like a Geiger counter. So you may have seen in videos, maybe in Monsters, Inc., when the child protection squad or whatever comes in, they're dressed in this crazy looking suit and holding these devices. This is a Geiger counter, and basically it picks up radiation. It can detect beta particles, it can detect alpha particles, and it can detect gamma rays, and it will tell you how many of those things are hitting this device per second, and therefore how much radiation there is in the room. Now, you do have some homework questions based on this, and here they are. So go ahead and answer these questions and have them ready to turn in tomorrow.